Hey Rachel, I hope you can hear me. So you're asking about lattice energy. Lattice energy is the energy that is required or that is used to hold an ionic compound together in the solid state. And there are two things that are going to result in a bigger lattice energy. One of them is the charge, and the charge is usually the biggest issue. So the higher the charge, the bigger the lattice energy. Okay, that's the first thing. The second thing is also size. The smaller the molecule, or the smaller the ions, then the bigger the lattice energy. And that's because their nuclei, those protons, are actually quite close together. And they're pulling on the electrons of the other ion. And so let's look at these couple of things real quick. So here's a problem. In each row, pick the compound with the bigger lattice energy. Okay, so let's look at these. So we have magnesium sulfide or sodium sulfide. Well, let's look at the two things. Charge is the biggest. So on the magnesium, then you have a +2. If you don't know how to find out what the charge is on that magnesium, then we need to talk. Magnesium has a +2. The sulfide has a -2. So those are charges. And sodium has a +1 charge, whereas the sulfide has a -2 charge. So based on what I said, then the magnesium has a +2, the sulfide has a -2, the sodium only has a +1, so it's definitely going to be the magnesium sulfide. Okay? So down here, lithium fluoride, the lithium has a +1, the fluoride has a -1, versus lithium oxide. Okay, the lithium has a +1, the oxide has a -2. So in this case, it's going to be the higher the charge on the lithium oxide. Let's look at this last one. We have beryllium chloride versus calcium chloride. Well, the charge on the beryllium is a +2, the chloride's a -1. Over here on calcium chloride, it is calcium that has a +2, a -1. So the charges between the two are actually the same. So we can't distinguish based on charge. But let's look at the periodic table real quick. I'm going to pull one up here, hopefully. Okay. Notice how the beryllium is going to be smaller than the calcium. I know it's smaller because it's higher up the periodic table. These molecules, these atoms, these elements are smaller up here. So remember, the smaller the atom, the higher, if you're comparing, then the higher the lattice energy. And so it's going to be beryllium chloride in this case, because beryllium is above calcium on the periodic table. So I'm going to click on check. I'm sure we got those right. Okay, let's just quickly look at a couple more examples that'll help you here. Okay, it's again the same lattice energy. We have strontium iodide and strontium chloride. Now the strontium's a +2 in both molecules. The iodide in this case is a -1 and the chloride is a -1. So those are the same in charge, so we have to look at the periodic table. Okay, so we have chlorine is right here, the chloride is right here, whereas the iodide is down from it. And so in this case, because chlorine is above the iodide, then the stronger lattice energy is going to be there. Okay, we have lithium sulfide versus cesium sulfide. This is a similar case as above. Lithium is a +1, cesium is a +1. Sulfide's a -2, sulfide's a -2 over here. Okay, so lithium versus cesium. Lithium definitely is way above cesium. That's going to have the stronger lattice energy. You have calcium bromide versus potassium bromide. Calcium's a +2. Again, if you don't know how to figure out that's a +2, Rach, we need to talk. And then the potassium is a +1. So plus, we have calcium +2, bromine -1. We have potassium +1, and the bromide is a -1. Since this has the higher charge, it's definitely going to be here. Going to check, then we're going to be right. So that should help you, I think, with those problems that you sent me. It should be very, very clear pretty obvious. They're not, shouldn't ask you anything that tricky.